Hi guys, not many, it's only two of you here. Only, I hope it's a record. It's a record for low attendance. Maybe the students are thinking they're on strike or something. I mean, I've never participated in strikes, so anyway, today we're going to start on a new topic, which is copula. You may know this or you may not know this. A copula is a function that's used to describe the dependence between two or more random variables. So if you have a random variable x comma y, right, then there are situations where the x and y will be dependent on each other, right? So for example, if you take this example where x is oil price and y is car price, and clearly they are dependent variables. If you take this example where x is oil price and y is food price, again they are dependent random variables, right? So a copula is used to model the dependence between two or more random variables. But in this course, I will only talk about the case of two variables, right? So for two variables, a copula is, loosely speaking, is a function from the unit square to the unit interval. So this is the unit square, and this is the unit interval, right? And it must satisfy these two conditions. That is, the marginals must be uniform 0, 1, right? That's what these two means. So this is kind of a loose definition of a copula. I will give a more formal definition of a copula later on. Okay. Okay. Now, before that, I'm gonna talk about two statements. Statement 1 and statement 2. Now, suppose you have a random vector x comma y with joint CDF. This is the joint CDF, and these are the marginal CDFs. Statement 1 says that for every joint CDF, there is a corresponding copula. And this is the proof of it. It's easy to prove because, all right, you start with the joint CDF, which is this. This is the notation for the joint CDF, and the definition is the probability that capital X less than equal to X, capital Y less than equal to Y. Now what I have done in this step is to take on both sides of this inequality, apply the function capital Fx on both sides, where capital Fx is the marginal of X, marginal CDF of X. And similarly, on both sides of this inequality, oh, it's not so bad. Welcome. Good morning. So on both sides of this inequality, apply the marginal CDF Fy. Okay. Now I don't know. You must have done this. You must probably in the first year undergraduate course on probability. Do you know there's something called the probability integral transformation or transform, which says that you should take the CDF of a random variable, then that's a uniform random variable. You remember that or not? Maybe you forgot, right? Anyway, just to refresh your memory, this is known as the probability integral transform, which says that the CDF, if you have a variable x, right, and then you take f of that variable x, where f is the CDF, right, then that becomes a uniform variable. So that's what I have applied that to get from this to this, and the same thing from this to this. Now what you have here is a copula, right? A copula with uniform marginals. So it must be, so you can write this as C of fx of x and fy of y. So I have proved the statement. The statement that I wanted to prove is that for every joint CDF of a random vector x comma y, there is a corresponding copula C, and I have proved it. If you're just coming in, we are just talking about copulas, okay? All right, so this is statement 1. Statement 2, let me take this away. Statement 2 is this: for every copula C, there is a corresponding joint CDF x of x and y, right? So to prove this, you start with C of u comma v, which by definition is this, right? Remember, the definition of a copula is a function from a unit box to a unit interval with uniform marginals, right? Okay, so it's this. What you have is this. Now, in the next step, from this line to this line, what I have done is to apply the inverse function of x to both sides of this inequality. So I'm taking the inverse function of x on the left and the inverse function of x on the right hand side, okay? And similarly to this inequality here, I applied the inverse function of y on both sides. So inverse function of y to this and the inverse function of y to this. Now, once again, by probability integral transform, I mean, this is something you should have done a long time ago. Maybe you forgot, maybe you did not. It says that anything of this kind must be equal to x, right? That is, if you take a inverse function, sorry, the inverse CDF of a uniform variable, then that must be the original variable x, right? And similarly, this guy here must be equal to y. All right, so this reduces to this because of the probability integral transform. And finally, what you have here is a joint CDF between x and y at these 2 points. All right, so I have proved that for every copula C, there is a corresponding joint CDF. So the statement goes both ways, right? For every joint CDF, there is a corresponding copula, and the other way around too, that for every copula there is a corresponding joint CDF, right? So, okay. All right. So those are statement 1 and 2. The next thing I'm going to talk about, where am I? Sorry, about lesson. Okay, two simple copulas. Okay, 2 simple copulas I'm going to talk about. The first of them is known as the Independent Scopula, right? And the Independent Scopula is defined as, hi Veronica, thank you for coming. I'm not on strike. Yeah. Okay, so the independent copula is given by this equation that C of u comma v is u times v. Now, let me explain why it is referred to as the independent scopula, right? Okay. First of all, this is equivalent to this statement here by definition, right? By definition, C at u comma v is this, right? The next thing I'm going to do is I'm going to take the inverse function of x on both sides of this inequality, so it becomes this, yeah. And similarly, I'm going to take the inverse function of y on both sides of this inequality, so it becomes this. We are talking about copulas, yeah. Okay. Now, once again, by the probability integral transformation or transform, what you have here is equal to x, and what you have here is equal to y, right? So this becomes equal to this. Now let let this be denoted by little x, and let this be denoted by little y. All right. Okay, so then this guy here reduces to this, where u, because x is equal to this, u must be the CDF of x at x. And because y is equal to this, v must be the CDF of y at y. All right, so this equation here becomes this. Now, what you have here on the left-hand side is the joint CDF of x and y, yeah, equal to the product of the marginal CDFs. So what I have shown is that this statement here is equivalent to this statement. And this statement is the usual definition of independence of two random variables. You probably know this from a long time ago, that you say that two variables x and y are independent if the joint CDF is the product of the marginal CDFs. Now what I have shown here is that this statement here, right, is equivalent to, in terms of the copula, is equivalent to this statement. Okay? Yeah? You guys okay? Right. The next thing, so that's a special copula, a simple copula. The second simple copula is known as the completely dependent copula, right? And is defined by this: is C of u comma a u comma v is equal to the minimum of u comma v, right? Now I'm going to show you that this statement is equivalent to this statement at the bottom. So the process is the same. So the first step is to write down the definition of C at u comma v, which is this, yeah, okay, equal to the minimum. And the next step is to take on both sides of this inequality the inverse function of x, right? And again, on the both sides of this inequality, the inverse function of y, yeah. All right, now again, by the probability integral transform, what you have here is equal to x, and what you have here is equal to y. Okay? You guys following me? All right, so that's then, all right, the next line, I'm going to let this guy here be equal to little x, right? And this guy here be equal to little y. So this implies that u must be the CDF of x and v must be the CDF of y. Right? So this statement here reduces to this statement here. Okay. And finally, the left-hand side is the joint CDF of x and y, and the right-hand side is this. And this, if you don't know this already, this is the usual definition of complete dependence between two random variables x and y. So you say two variables are completely dependent if the joint CDF is equal to the minimum of the marginal CDFs. Right, so as you can see, what I have shown you is that this statement is equivalent to this statement, right? All right, so that, excuse me. So that's some properties. Okay, the next is the formal definition of a copula. So you say a function from the unit square or unit box to a unit interval is a copula if it satisfies these 6 properties. So the first property is that C at u comma 0 is 0 for all u, C at 0 comma v is 0 for all v, C at u comma 1 equal to u for all u, C at 1 comma v is equal to v for all v, and the partial derivative of C is non-negative for all u and v, and the partial derivative of C with respect to v is also non-negative with respect to all u and v. I did some examples. I hope you looked at this example. I mean, this is a trivial example. This is the Independent Scopula, you may recall, right? Yeah. And for this Independent Scopula, it's easy to see that all 6 properties are satisfied. Yeah. Okay. Hence, C is a copula. Okay. So that's one example I did. The second example I did this is the second example I did in the videos. So this is the completely dependent copula, and once again it's easy to see that all 6 properties are satisfied, and hence C is a copula, right? And the third example, this is the third example I did. Yeah. So once again, it's not difficult to say. But theta is a number between -1 and +1. It's not difficult to see that all 6 properties are satisfied. Okay. All right. So that's the 6. Okay. The final section of the video was this. It's about the 2 most popular copulas that there have been, or there are. The first copula is the normal copula, also known as the Gaussian copula, and is given by this equation here, right, where phi denotes the CDF of the standard normal distribution. So that's these two. Phi 2 denotes the joint CDF of the standard bivariate normal distribution, right? There is an interesting story about this copula thing. I explained that in the video, I believe, but it has been the most popular. I mean, it has been the most popular copula, but it's no longer the most popular copula because of what happened in 2008. You remember that in 2008 there was a big. I hope you guys were. Yeah. You were born before 2008, right? Or no? Yeah, I'm sure. Yeah. 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 Okay. Probably you remember. I don't know. So clearly, there was a big financial crisis in 2008, and a lot of people lost a lot of money. Even the Wall Street was affected. When you think about Wall Street, you think that is is the biggest financial institution in the world, and all the people working in Wall Street, you would think that they are the greatest people in the world, but they didn't know some simple stuff, that they were using like the Gaussian copula to model financial data. But the Gaussian copula is not a good model for financial data, especially in the tails. It can give very bad fits, and they did not know that at that time. Okay, so, and that's how this. I think I gave a copy of this paper. There was a paper that was written about this. This is the paper. You might have seen this in this paper. It says the formula that killed Wall Street. Is the formula that it talks about is the Gaussian copula. So it says the use of the Gaussian copula led to a lot of crash, the markets crashing around the world, not just in Wall Street. So you should look at it. I don't know whether you had a chance to read the paper, but you should look at the second page or the third page. This formula here is the formula that I just wrote down. This is the Gaussian copula. Yeah, so I mean, it's a simple fact. I mean, you don't need to have a PhD. I mean, all the people working for Wall Street, they have PhDs from, top schools like Harvard, so Stanford, MIT, and all the big universities. But and yet they didn't know this simple fact that the Gaussian copula is not a good model for especially in the tails. It can give very bad fits. Yeah. So any prediction that you make, especially in the tails, can be very wrong. Okay. All right. So that's the story behind this copula. So since 2008, there have been many papers written about finding new models for copulas, right, that are more realistic when it comes to fitting financial data. Yeah, and one of the models that's been popular. Let me fish it out. One of the models that has been popular is the T-Copula. Students T-Copula, and is given by this equation here. Given by this equation, where this guy here denotes the CDF of the students T distribution. I'm sure you guys know the students T, right? This is the CDF of the univariate students T distribution with degree of freedom A, and the capital T2 is the joint CDF of the bivariate students T distribution with degree of freedom A. And the T-Copula is a much better model for financial data than the Gaussian copula. The Gaussian is not at all a good fit. I mean, the T-Copula gives much better fit, especially in the tails of the data. Like, okay, so people have been using the T-Copula since the crisis occurred, and there have been other models proposed in the literature too. It's not just, you will see, especially if you want to do a PhD or something, there are papers written constantly about copulas, new models for copulas, that are better than which are better than the Gaussian copula. So there are like hundreds of papers on this area. Okay, they're constantly written about it. Okay, so that's all I want to say about this section on copulas. So in the remaining time, we can do some examples. Unless you guys have any questions you want to ask me. Robert, are you okay? Any questions you want to ask? All right, so let's do some examples. All right, we will do more examples on Friday when we meet. So example 1. You mean this one? There's only one guy here. I don't know what happened to the rest. All right, guys. So show that this is a copula. So you need to check all this. Remember, there are 6 properties that we need to check, right? So property 1 is that C so you put U2 equal to 0. Now what is 0 to the power minus alpha? Remember, alpha is a positive number, so 0 to the power minus alpha is infinity, right? So infinity plus anything is infinity. So infinity to the negative power, and this is 0. You follow me? Yeah? Alright. So this property is satisfied. The second property again, this guy here is infinity, right? So it's infinity to the power negative power, which is 0. Okay, so property 2 is satisfied too. Property 3 is you put U2 equal to 1, right? So this is gonna be U1 minus alpha plus 1 minus 1 to the power minus 1 over alpha. Alright, so this is equal to U1. Yeah. Alright, so that's satisfied too. Alright, this is satisfied. You guys okay? Any questions? Let me know, guys. So the first four properties are trivial. I mean, easy to check. Yeah? It's only the last two properties can be tricky sometimes. So the property number 5 is to find the partial derivative with respect to U1, right? So if you differentiate this with respect to U1, what do you get? You get minus 1 over alpha yes. Oh, sorry. Alright, multiplied by the derivative of this, which is minus alpha times U1 minus alpha minus this. So minus 1 over alpha multiplied by minus alpha is 1. So this is you get this, yeah? And this is clearly non-negative, right? Because this is non-negative and this is non-negative. So property 5 is satisfied. Okay. And property 6 is similar. So property 6 will be you differentiate with respect to u2, right? So you get minus all right, and this is, I mean, this is equal to this is clearly non-negative. So all 6 properties are satisfied, and hence C is a copula. Okay, guys, this is easy, right? Next one, I've got some more questions here, just some more. So this is the one we just did. Oh yeah, one more. Are you guys okay with this? This is okay. Example 2. Oh, sorry. Example 2 is this one. So show that the function given by this is the minimum of u1 comma u2 to the power theta, u1 comma u2 to the power 1 minus theta, where theta is a number between 0 and 1, is is a copula, right? So can you try this, please? Can you do this? So part 1, so if you put u2 equal to 0, you get the minimum will be, all right, let me write it down. The minimum will be this, then u1 times 0 to the power of this, and this is clearly equal to 0. Okay, and part 2, if you put u1 equal to 0, you get you get 0 times u2 to the power 1 minus theta. Yeah, and which is once again equal to 0. All right. Property 3. You should put u2 equal to 1. You get minimum of u1 comma 1 then 1 times u is u1 to the power 1 minus theta, the minimum of u1 and 1 is u1, because u1 is a number between 0 and 1. So this is going to be equal to u1. Alright guys, are you okay with this? Yes, so this property is satisfied too. Property 4, if you put u1 equal to 1 into this, you get u2, and this becomes u2. Okay guys? Alright, so the first 4 properties, as I said, they're trivial. So it just, when you do the last 2 properties, you have to be a little careful. So somebody just come in. When you do the last 2 properties, because you have a minimum here, I think it's best to consider the 2 separate cases where u1 is less than u2 and u1 is greater than u2, right? So what I'm going to do is this. Sorry. I'm going to consider 2 cases, right? Case 1, when if u1 is less than equal to, if u1 is less than equal to u2, right, then the minimum will be u1, right? So it will be, you should do the working, it will be u1 times u2 to the power 1 minus theta. And if u1 is greater than u2, the minimum will be u2, right? So if you do the working, it will be u1 like this. Okay? You follow me? Okay. I mean, you should just do the math for this, right? This you will get one of this depending on whether u1 is less than or equal to u2 or u1 is greater than u2, right? Okay, so now you should do the partial derivative with respect to u1. You will get this, and you get this, right? Okay, and clearly this is non-negative, and so is this one, because theta is a number between 0 and 1. So this is greater than or equal to 0, and therefore condition 5 is satisfied. And similarly, can I take this away? Yeah, okay. For condition 6, right, you're going to do the partial derivative for the 2 cases. So the case 1 is case 2 is is this, right? So if you take the partial derivative with respect to u2, this is what you will get. You will get 1 minus theta times u1 times u2 minus theta, and u1 to the power 1 minus theta. Yeah, and both these are non-negative. Alright, so this greater than or equal to 0, hence okay guys, so this completes example 2. Any questions on this? One more example, let me check if I can find some examples here. Oh yeah, here we are. Alright, example number 3, may not have time. I would just give it to you. If I don't have the time, just I'll let you finish it. So this is example 3. Show that C Alright guys, can you try to do this please? So theta is a number between minus 1 and plus 1. Sorry, excluding 1. So it should be not including 1, excluding 1. Includes minus 1 but not includes plus 1. Okay. Alright, so part 1 is to show that this is, if you put u2 equal to 0 is clearly 0. Sorry, u1 should. And part 2 is if you put u1 equal to 0, part 3 is C u1 comma 1. So you put u2 equal to 1. So it's gonna be and this is clearly equal to u1. Okay, and part 4 is you put u1 equal to 1, you get 1 times u2 divided by 1 minus theta times 1 minus 1 minus u2, so you get this to be equal to u2, which is what you expect. And part 5, alright, part 5 you need to, because you can use the quotient rule. I'm sure you guys know the quotient rule for differentiation, because you have a quotient of two functions, so you have to use the quotient rule for, so if you use the quotient rule, this is what you will get. Correct me if I'm wrong. You get theta u2 times 1 minus, it's a little bit complicated, but I'm sure you know the math. This is the first thing you get. The second thing is minus theta u1 u2 1 minus u2, right? This is what you get in the numerator, and in the denominator you get this. So it's using the quotient rule, right? And if you simplify this, guys, you will get u2 1 minus theta 1 minus u2, yeah, divided by 1 minus theta 1 minus u1 1 minus u2 squared. Now clearly 1 minus u2 is a number between 0 and 1. Theta is a number between minus 1 and plus 1. So this guy, where's my, okay, this guy must be non-negative, right? Because 1 minus u2 is a number between 0 and 1, and theta by definition is number between 0 and 1, sorry, minus 1 and plus 1. So this is non-negative, this is non-negative, this is non-negative, so this is satisfied. And 6 is similar. I'm run out of time. Similar to part 5. So hence C is a copula. Alright guys, sorry. So did you follow this? Yeah? Okay. Yeah, 0 and 2, yeah. Yeah, it's not, it depends. Yeah, if theta is minus 1 and u2 is 0, then it will be 2. And if theta is plus 1 and u2 is, it will be 0, yeah. So it is 0 and 2, yeah. The range is from 0 to 2, yeah. Yes, you're right. In any case, it's non-negative, so that it's, you just need to check whether it's non-negative. That's all. Yeah. All right, guys. Thank you for handing in quiz 7. It seems I think all of you got it correct, but it's quite a few people had made mistakes. I don't understand why. Simple. I can't understand why they make simple mistakes. I don't know. I will check it. I will do the marking later on. All right, guys. So see you on Friday for the tutorial. You take care. Robert, you want to see me today? No. Sorry?
How long was the strike?
I have no idea. Is your other forces affected or not?
Yeah.
They are? So it's the lecturer strike? Oh, sorry.
But how long is it gonna be, like all this week or only?
I have no idea. I mean, I don't know. I'm not. I just don't follow the news for this because I don't see why they are striking. I just don't know. I don't know why. So
I was told that two teachers, like they are, there's a telling them to stop working here. And that's why they are doing the strike, so they are,
I think it's about the pay or something. It's about the pension. I think is it. I think it's about the pension.